Hello everyone, welcome to this online course on material science. I am Dr. Imtiaz Ahmed. I believe this is lecture 15 in module 1 on magnetism. If you recall, in the last lecture I discussed the Langevin model of paramagnetism, and I'm following this book Magnetism in Condensed Matter from Stephen Blundell. And if you remember that I derived the expression for the ratio of the magnetization of a paramagnetic material to the saturation magnetization, right, as a function which is known as the Langevin function, right? And the parameter in the argument was y, and we remember the y is nothing but the ratio of magnetic moment times the magnetic field divided by Boltzmann constant times the temperature, right? And we also remember the Langevin function has a functional form in terms of the y, which is given by the cot hyperbolic of y minus 1 by y, right? Let us try to understand the behavior of this function to understand the magnetization, right? Because on the right hand side of this expression we have this function. So let's plot m by ms, right, which is the Langevin function, as a function of y, right? That's our y, mu b by kbt. You can see it from here. So we are plotting the Langevin function as a function of y here. Now you can see that this is a unitless number, right? So that's why we don't have any unit in the x-axis. And when the magnetization hits the maximum value, that's +1. And for negative magnetic field, we have the -1, right? So moments align in the negative B field direction. So +1 and -1, those are the maximum magnetization value achievable in magnetic field in the +z direction and magnetic field in the -z direction, right? Now, if you look at this picture, right, we are plotting first, let's say, a linear approximation, right? So that's the linear function in this dotted line. And then on top of it, I am plotting the original Langevin function, right? That's our Langevin function. Now you can see that in some region here, the Langevin function and the linear one is the same, right? So in this region, can you see that this quantity is small, right? And this y, when small, the b has to be small. So this is a low field limit, right? When the low magnetic field is applied, you can see the Langevin function can be approximated by a linear function. That's point number 1. And point number 2 is that, so now you are going away from this low magnetic field in positive magnetic field direction, or maybe in the negative magnetic field direction, right? You can see the curve is kind of bending, and then if I can extend this curve, let's say, it will trying to reach the saturation level, right, at some very high magnetic field like this way, right, just to make it more clearer. And then on the negative applied field direction, it will reach in high magnetic field, right? So this is indicating that it's getting difficult to align all the moments. And you remember why? Because the field energy needs to fight against the thermal fluctuation energy, right? Because the thermal fluctuation is trying to disrupt the alignment due to the magnetic field, due to the alignment of the external magnetic field, right? So that's number 2, and let me show you how to explain this linear regime, and from which the Curie's law, the famous Curie's law that you have seen in your first year physics courses maybe, will arrive, right? So for that, let us expand the Langevin function here. So the Langevin function is nothing but cot hyperbolic 1 by y. Now you know the cot hyperbolic function can be expanded in a series expansion, and if you look at the literature, it's nothing but 1 by y then we have y by 3, then some more terms. The leading term is of the order of O cube, right? Y cube. So that's the approximation for the cot hyperbolic function. Then we have 1 by y, right? You can see this 1 by y cancels each other, and we have y by 3 and some terms of the order y by 3, right? And you can see we are trying to understand the behavior of the function in the regime where this y is small, right? So if the y is small, the y cube is even smaller, then we can neglect this term, right? So in that regime where the y is small, we can approximate the Langevin function by just a linear function, right, which is y by 3. That's our understanding, and we know what this Langevin function is, right? That's the ratio of the magnetization of the material to the saturation magnetization, right? So from this, you can see what is the value of m. That's like 1/3 ms y by 3 y, right? So we have 1/3 already here. So do you remember what is the value of ms? That's like number of magnetic dipole moment per unit volume times the magnetic moment, right? And what is the value of y? Y is nothing but the magnetic moment times the magnetic field divided by the Boltzmann constant and the temperature. So from this you can find out a ratio of magnetic field, magnetization to the magnetic field, which is nothing but 1/3 mu square, right? And then you have kBt and n, right? If I'm not wrong, that's the expression for the ratio m by b. Now remember that from the lectures in the beginning that we define the susceptibility of any material by mu naught is the free space permeability and then m by b, right? So we know the ratio m by b from here, so let's put the value there. So then the susceptibility of the paramagnetic material becomes mu naught, then we have 1/3 mu square n by kBt, right? So let me rewrite this expression in the next page and show you how this is the Curie's law, right? So we have the susceptibility, let's say for a paramagnet, is 1/3 n mu naught mu square divided by kBt, right? And if I write all of these as a number and denote it by C, and in subscript I put the Curie to honor Curie, the inventor of this magnetism, divided by T, right? So this is the famous Curie's law where it says that the susceptibility of a paramagnetic material goes as inverse of the temperature. So as you increase the temperature, susceptibility goes down. Physically, what it means that at high temperature, the material's susceptibility is getting smaller, which means it is becoming difficult to align the magnetic moments inside that solid by applying an external magnetic field. And you know why this is the case, right? Because the thermal fluctuation, as your temperature is going up, the thermal energy is disrupting the alignment of the moments, right? That's why it's getting harder and harder, right? So that's your famous Curie's law. So I have shown you how the Langevin model will produce you the Curie's law in the low field regime, right? And in the next lecture, my plan is to show you how this discussion of paramagnetic model can be modified considering the quantum mechanical consideration, right? And then we will see how the function changes into different forms. I think that's about it, and thanks for listening.